Welcome to MSN Digit Max. I am S. Shubha, Assistant Professor, Department of Mathematics, Madurai Sivagasi Nada's Pioneer Meenakshi Women's College, Uvandi. Here is a learning resource for Abstract Algebra, Unit 1, Module 7. In the previous videos, we covered the topics, definition for groups, and examples for groups. In this video also, we will see some more examples for groups. Before going to start, let me recollect the definition for groups. G is a non-empty set together with the binary operation star which satisfies the conditions. Number 1. The binary operation star is associative. Number 2. G has an identity element E. Number 3. Every element in G has an inverse in G. Let me start with the first example. Let me take A be any non-empty set and B of A be the set of all bijections from A to itself. That is, B of A equal to set of all F such that F from A to A is a bijection. First, let me prove star the composition of functions becomes a binary operation on this set B of A. For this, let me take two elements from B of A, F comma G. Then F from A to A and G from A to A are bijections. By the definition of composition of functions, for any A belongs to A, F composite G of A is equal to F of G of A. We know the result. Let F from A to B and G from B to C are bijections. Then G composite F from A to C is also a bijection. Since F and G are bijections, then F composite G is also a bijection. Therefore, F composite G belongs to B of A. Next comes associative property. Here also we will use the result F from A to B, G from B to C, H from C to D are functions. Then H composite G composite F equal to H composite G composite F. By using this result, the composition of functions becomes associative. Then identity property. Here also we use the result. Let F from A to A be any function. Then F composite IA equal to IA composite F equal to F. Here IA is a function from A to A defined by IA of X equal to X for all X belongs to A. Yes, that IA is a bijection from A to itself. Therefore, that IA belongs to B of A is the identity element. Then inverse property. Let F from A to B be a bijection. Then F inverse from B to A is also a bijection. And F inverse composite F equal to IA and F composite F inverse equal to IB. From this result, F inverse from A to A is also a bijection. Therefore, for any F belongs to B of A, there must be an F inverse is a bijection that also belongs to B of A. Hence, B of A is a group under composition of functions. Before going to see next example for group, let me introduce a definition, that is a notation Zn. Zn is equal to the set of all elements which starts from 0 and ends with n minus 1. Here we introduce a few binary operations plus circle and dot circle. For this, let me take two elements a comma b belongs to Zn. Then a plus b equal to Qn plus r, where 0 less than or equal to r less than n. We define a plus circle b is equal to r. Likewise, a into b is equal to q dash n plus s, where 0 less than or equal to s less than n. We define a dot circle b is equal to s. The binary operations plus circle and dot circle are called addition modulo n and multiplication modulo n respectively. In this way, we define two binary operations plus circle and dot circle on the set Zn. For this definition, let me give an example Z7. Z7 equal to set of all 0, 1, 2, 3, 4, 5, 6. Here we take 2 and 4, then 2 plus circle 4 is equal to number 6. Likewise, 4 plus circle 5 equal to 2. That is, to find 4 plus circle 5, we have to add 4 and 5, which is equal to 7. Then we have to divide 9 by 7. We get the remainder 2. Therefore, we get 4 plus circle 5 is equal to 2. Likewise, 1 dot circle 2 equal to 2 and 3 dot circle 2 is equal to 6. In the previous slide, we introduced the new set Zn and two binary operations plus circle and dot circle. Let me start the example. Here we are going to prove Zn plus circle is a group. Then we take Zn equal to 0, 1 to etc. up to n minus 1. From the definition of plus circle, clearly it is true that a plus circle b equal to r belongs to Zn. Let me check the associative property. For this we have to take three elements, that is a, b, c belongs to Zn. Let me take three equations. A plus b equal to Qn plus r1, where r1 lies between 0 and n, and b plus c equal to Q2n plus r2, and r1 plus c equal to Q3n plus r3. Here r2 and r3 both lies between 0 and n. We add a plus b and then c. From equation 1, a plus b can be written as Qnn plus r1 plus c. By using equation 3, Qnn plus Q3n plus r3. Therefore, a plus b plus c equal to Q1 plus Q3 into n plus r3. Likewise, a plus b plus c can also be written as a plus Q2n plus r2. We all know that addition of integers is an associative. Therefore, a plus b plus c equal to a plus b plus c, which implies q1 plus q3 into n plus r3 equal to a plus q2n plus r2. On simplification, we get a plus r2 equal to q4n plus r3, where q4 is equal to q1 plus q3 minus q2. Therefore, a plus circle b plus circle c is equal to r1 plus circle c, which is equal to r3. Likewise, a plus circle b plus circle c is equal to a plus circle r2, which is equal to r3. Therefore, a plus circle b plus circle c equal to a plus circle b plus circle c. Hence, plus circle is an associative. Next comes identity. 0 plus circle A is equal to A. Therefore, 0 belongs to Zn is the identity element. Inverse property. A plus circle n minus A equal to 0. Therefore, inverse of A is n minus A. Hence, Zn plus circle is a group. That is addition modulo n. and Zn forms a group. Then next example, here we take n is a prime number and Zn minus singleton 0 is a group under multiplication modulo n. Here we take the set as Zn minus singleton 0, which is equal to set of all 0, 1, 2, etc. n minus 1. Here n is a prime number. Let me prove the dot circle is a binary operation on Zn minus singleton 0. For this we have to take a comma b belongs to Zn minus singleton 0. Then ab equal to qn plus r, where 0 less than or equal to r less than n. Therefore a dot circle b equal to r. That r belongs to Zn. But we have to prove that a dot circle b is not equal to 0, because here we take the set as Zn minus singleton 0. Therefore, let me assume that a dot circle b equal to 0. Then ab equal to qn plus 0. That is, ab is a multiple of n. Then n divides ab. Since n is prime, from n divides ab, we get n divides a or n divides b. That is, a is a multiple of n or b is a multiple of n. But which is not possible because both a and b belongs to Zn minus singleton 0. Therefore, a comma b less than n. Hence, either a equal to 0 or b equal to 0. But it is not possible. Therefore, a dot circle b not equal to 0. Hence, a dot circle b belongs to Zn minus singleton 0. That is, closure property is satisfied. Next, associative property. Here we have to choose three elements A, B, C from Zn minus singleton 0. From the previous example, here also we can take three equations. AB equal to Q1n plus R1, BC equal to Q2n plus R2, R1C equal to Q3n plus R3, where R1, R2, R3 lies between 0 and n. Yes, AB into C equal to Qnn plus R1 into C. By using equations 1 and 3, we get Q1C plus Q3 into n plus R3. And A into BC also equal to A into Q2n plus R2. AB into C equal to A into BC. On simplification, we get AR2 equal to Q4n plus R3, where Q4 is equal to Q1C plus Q3 minus A into Q2. Therefore, we get A dot circle B dot circle C is equal to R3, and also A dot circle B dot circle C equal to R3. Therefore, dot circle is an associative binary operation defined on Zn minus singleton 0. Next comes identity. A dot circle 1 is equal to A. Therefore, 1 is the identity element. Next comes inverse. For this, let me take one element A belongs to Zn minus singleton 0. We are given that n is prime. Therefore, GCD of A comma n is equal to 1. Then from the result, the linear congruence Ax congruent to 1 mod n has a unique solution. B belongs to Zn minus singleton 0. From this result, A dot circle B is equal to B dot circle A equal to 1, where B got from the congruence Ax congruent to 1 mod n. Therefore, we obtain a element B. Therefore, that B is the inverse of A. Therefore, this set satisfies all the conditions. Therefore, Zn minus singleton 0 is a group. Next example. Here we take G is the set of all matrices of the form X, 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 X. That is, a matrix contains same elements. In 2 by 2 matrix, we take same x, where x belongs to R star. I am going to prove this G is a group under matrix multiplication. Let me start with the closure property. For this, we have to take two matrices. A comma B belongs to G. A equal to matrix x x x, B equal to matrix y y y, where both x and y belongs to R star. Let me multiply the two matrices A B equal to, which give you the answer. The matrix 2xy, 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 2xy. That also belongs to G. Therefore, AB belongs to G. We already proved that matrix multiplication is associative in the previous videos. Next comes identity. Here we have to select the identity matrix, which we name it as capital E is equal to the matrix E. We are going to prove AE is equal to A. Then AE equal to A gives the matrix XXX into the matrix EE equal to matrix XXXX. On simplification, we get 2EX equal to X. Therefore, E is equal to 1 by 2. Therefore, the matrix E equal to 1 by 2, 1 by 2, 1 by 2, 1 by 2 belongs to G is the identity element. Next, inverse. We have to find inverse for any matrix belongs to G. Let me take the inverse as y. Therefore, the matrix X into matrix Y is equal to the identity element, the matrix 1 by 2. On simplification, we get 2xy equal to 1 by 2. Therefore, y equal to 1 by 4x. Therefore, the inverse of the matrix XXX is the matrix 1 by 4x, 1 by 4x, 1 by 4x and 1 by 4x. Therefore, this G also satisfies all the properties of the group. Hence, G is a group. Then next example. Here we take G equal to set of all the ordered pairs A comma B, where the first element A belongs to R star, the second element B belongs to R. Here R star is the set of all non-zero real numbers. This G form a group under the binary operation star defined by A comma B star C comma D is equal to AC comma BC plus D. We are going to prove under this binary operation star, this G form a group. Let me start from the closure property. For this, we have to choose two elements A comma B and C comma D. Here both elements A comma C belongs to R star, B comma D belongs to R. Then we apply the binary operation star A comma B star C comma D equal to AC comma BC plus D. These elements are also belongs to G because the first two element AC belongs to R star, second element BC belongs to D belongs to R. Therefore, the newly defined star becomes a binary operation on G. Then let me check the associative property. For this, we have to collect three elements x equal to AB, y equal to CD, z equal to EF. First calculate the left side. X star y star z equal to A comma B star CE comma DE plus F, which is equal to ACE comma BCE plus DE plus F. Then right hand side X star y star z equal to AC comma BC plus D star E comma F, which is equal to ACE comma BCE plus DE plus F. Therefore, this star becomes a associative. Then identity. I am going to find the identity element. For this, we take A comma B star C comma D equal to A comma B. Then AC comma BC plus D equal to A comma B, which will give you AC equal to A and BC plus D equal to B. But we have to calculate the value of C and D. For the above two equations, C equal to 1, B plus D equal to B, which implies D equal to 0. Therefore, the element 1, 0 satisfies the identity property. Therefore, 1, 0 is the identity element. Then, inverse property. Here I am going to find A dash B dash, which will be the inverse of A, B. Then A, B star A dash, B dash equal to 1, 0. A dash plus B A dash plus B dash equal to 1, 0. On simplification, we get A dash equal to 1 by A, B dash equal to minus B by A. Therefore, the element 1 by A, minus B by A is the inverse for A, B. Hence, G, star is a group. Next example, N, that is set of all natural numbers. Here we define A star B equal to A. We are going to prove N, star is not a group. We proved several examples for group, but this one is an example for not a group. Therefore, we have to prove this N does not satisfy any one of the properties of the group. Yes, let me start from the first property. A, B belongs to N. Then A star B equal to A. Again, A belongs to N. Therefore, this star is a binary operation on N. And then, from the definition of star itself, it is clear that star is an associative binary operation on N. Next comes identity. Here we have to find the identity element in N, which satisfies the property A star E equal to E star A equal to A. But A star E equal to A and E star A equal to E. That is, both the elements are not equal. Therefore, we cannot find E which satisfies the identity property in N. Hence, this N, star does not have an identity element. Therefore, this N, star is not a group.